Welcome back, math scholars. It's time to finish up lesson 63.63. We're going to be doing some arc lengths today in relation to our discussion of the unit circle, and then kind of more on the, well, I guess it does have to do with the unit circle, but kind of has more to do with measuring the lengths around the outside of the circle. And so this discussion is going to come back around to radians. Back to radians. The beautiful thing here is that if I can get you to start thinking in terms of radians being rotations rather than degrees, then we will have gotten some success there. If you're going to take any more math beyond this, radians is the way to go. Radians gets used also in physics with rotational inertia problems, with figuring out the amount of rotational force involved in something. So radians is really a good call. Let's go back to our unit circle. The beauty of the unit circle is that it has a radius of 1. Okay, and that simplified a lot of things as far as triangles that go in the grid, and it also simplifies things about distances around the outside. We knew that if we took the point 1, 0 and we rotate it, we stop somewhere, that angle there, if it's given in radians, is also equal to the distance that we've gone around the outside. That is, if we went 1 radius worth on the outside, our angle of rotation is 1 radian, which comes out to be about 53 degrees, 53.1 degrees if you're going to divide the circle up like that. I don't want to just divide the circle up like that. I want to break it up into fractions of 360 degrees, or even better, fractions of 180 degrees. Because once we've rotated all the way over here to 180 degrees, we have rotated it pi radians. A little bit more than 3 radiuses around the circle to get halfway around the circle. And thus, by consequence, if we're on the unit circle, if we go all the way around the circle and we end up back where we started from, we have gone 2 pi radians, both in the angle that we've rotated, because 2 pi radians is equal to 360 degrees, and the distance we've traveled along the outside. We've gone 2 pi radiuses around the outside of the circle, so a little bit more than 6, about 6.28 radiuses distance around the outside. The key there was that the radius was equal to 1. Yeah, because we're measuring radians. So we end up having now a circumference problem. That's it, a circumference problem. The cool thing about radians is that they are, in a sense, unitless. If we kind of take out the whole radius issue there, then we don't need a special conversion unit to go from one type of measurement to another. We can just use radians. And I'm going to show you that here as we talk about arc lengths. We're not going to go all the way around the circle. We're going to go part of the way around the circle. And we would like to know how far that we've gone. This is going to be way easier to do. The math is much simpler if we only use radians rather than thinking of it in degrees. So have that unit circle out, and so you can compare what the degrees and the degrees and radians are on that chart. So arc-length problems are basically finding fractions of the circumference. And as you recall, that's our nice way of saying, I'm thinking you already know this, circumference equals pi times the diameter. But that diameter thing doesn't really help, does it? Unless we're thinking in terms of tau, but we're not. We're thinking in terms of pi. So we already know that the diameter is twice the radius. So let's just replace that d with 2r. And then let me rearrange this equation a little bit to make it a little bit cleaner. We've got 2 times pi times r. That's the circumference of a circle. Now, what's the circumference of the unit circle? The unit circle has a radius of 1. So this r turns into a 1. And then since it's a 1, we can basically ignore it. And we have that the circumference of the unit circle is 2 pi radians. Okay, now if we want fractions of the whole circumference, we would just be multiplying by something compared to, well, if we were doing degrees, we'd have to say something compared to 360. So let's say we go 120 degrees, we have to multiply 2 pi radians by 120 degrees and then divide by 360. But if we're doing this in radians, we could have a better conversion here, couldn't we? We could just have that we're looking at the whole circumference and then we're finding the fraction. So let's say that we're at, say we're at 90 degrees, right? 90 degrees. 90 degrees is what in radians? Look at your chart, figure it out. It's up there at the top of the circle. It's pi over 2 radians, is it not? Okay. So we've got that compared to 2 pi. Now you can see right away that if I do this conversion thing, this is the fraction of the circumference here. This is 90 degrees out of the whole 360 degrees. That the 2 pi radian for the whole circumference and the 2 pi radian of my conversion unit are going to cancel out every time, every single time. So what's the deal here? How's that help? Because if we went back to our original formula of 2 pi times the radius, if we would like to convert a section, an arc length, a sector, well, it's actually just an arc length of this, to find the distance around the outside of this thing, all we need is what's left. We need to know how big the radius is, and we need to know what angle we're rotating it in radians. The 2 pi's will cancel out. We don't even need it. So if we want to find arc length, which is given, instead of C for circumference, it's given the letter S for, like, it's a section of the whole thing. Then all we need is the radius, and we need the angle in radians. That's it. This is the math of least resistance. This is the quickest way to get to an answer, is to think in terms of radians. So yeah, an example in the book, it's got a circle, and this circle has a circumference, or sorry, has a radius of 5 centimeters. 5 centimeters. And they would like to know what is the arc length if we rotate through 2 pi over 3 radians. So we end up somewhere over here. We want to know what's this distance here to get to 2/3 pi radians. Now I knew it was over there because I know that 1 whole pi gets at me here, so it's 2/3 of the way there. If you'd like to translate that for yourself on your unit circle, you can see that that's 120 degrees. If we were going to do it the long way, we would have to know what the whole circumference was. We'd have to go 2 pi times 5 for the whole circumference, and then multiply that by 120 degrees compared to 360 degrees. That would be what you'd have to do if you did it in degrees. It's not super hard, but if we're going to do it in radians, here's what we do. 5 times 2 pi over 3 equals 10 pi over 3, and then our units. Here we go. We keep it exactly like that. If you'd like an approximation, use that pi button on your calculator, but you don't need to. That's a correct answer. Some of you are curious though, so let's look at that. Let's go 10 pi divided by 3. And you know that pi is close to 3, so my answer should be close to 10. 10.47 centimeters. This is useful for me as I'm measuring things out on the track. I have that wheel, okay, and it has a circumference of 1 meter exactly. It's pretty easy to figure out. And every time I go around, that's 2 pi radians. 2 pi radians equals 1 meter for the whole circumference. So in designing that, they need to know, I need the circumference to be 1 meter, and then you're doing rotations. It clicks every single time it goes around. So this is the magic formula for you today. R times my angle in degrees. That's a beautiful way of doing it. Sorry, radians, angle in radians. That's the quickest way to get these ones done. Now, there's one question in there. I think that they start off with the thing in degrees. They got a circle. It's got a radius of 2.5 feet or something like that, and they want us to rotate that 225 degrees. And they want to know what's that distance to get to 225 degrees. Go pull out your unit circle and go figure out what 225 degrees is in radians. Okay, just go straight over from the degree thing to the radian measurement. What is that? It's an extra 45 past 180. So that's 5 pi over 4 radians. And now that we've got the angle in radians, we just multiply that by its radius, 2.5, or what's that as a fraction? 2.5 is 5/4. No, that's not right. 5/2. No, 4. Yeah, it's 5/2. Makes the math a little nicer. We've got 25 pi over 8. And then our units, we take off the radians, our units are in feet. And we're going to leave it like that because that's an exact answer. Or if you want to, you can use your pi button on your calculator to get exactly what it is. That should be enough to help you finish off your lesson. If you can stand on Jupiter, you can do that problem. But that should be enough. As well as that, I'd like you to push some buttons on your calculator for Lab 10. That will get you ready to go for our next discussion about logarithms. Stay tuned for that. It's coming later this week. Until then, stay healthy, wash your hands, and don't do anything that you'd be embarrassed of telling your grandmother about.